Okay, everyone, this is section 7.2. In this section, our goal here is to be able to graph and use exponential decay functions. So some vocabulary: an exponential decay function is decay if a is greater than 0 and the b is between 0 and 1. So then the function y equals a times b to the x is exponential decay with a growth factor of b. Okay, and the decay factor is the quantity b in which the exponential growth function y equals a times b to the x, with a being greater than 0 and 0, or b being in between 0 and 1. So basically, if b is a fraction that is less than 1, so like 1/4, that is decay. But just because it's a fraction for b doesn't mean it's automatically decay, because we can write whole numbers as fractions as well. So like 12/4 is the same thing as 3. So even though it is a fraction, it is not decay because it's still bigger than 1. Okay? So the parent function for exponential decay functions fall from left to right. Okay? They still have a y-intercept and an asymptote. Okay, so the domain of f of x equals b to the x power is all real numbers, and the range is y is greater than 0, because our asymptote is the x-axis. So in example 1, we're first going to graph this exponential equation, and again we're going to do this by making a table. So if we go to the graphing calculator and go to y equals and put in our equation 1/2 raised to the x power, and second table it, well, here's our table of values. Okay, and if we keep going down, it's getting very, very close to 0, so our asymptote's going to be at 0, and we could just use -2 to 2 to make our table of values. So here's our table. We'll use -2 to 2. And at -2, it was 4. -1 was 2. At 0, it was 1. At 1, it was 1/2. And then at 2, it was 1/4. And if we go and graph this, -2, 4. -1, 2. 0, 1. 1.5. And then 1/4. And even if you wanted to go to -3, okay, at -3, it was 8. So at -3, 8, that would even give you a point higher than 4. And if we were to keep going in the negative x direction, we would be getting bigger in the y's. Okay, so here's our decay falling graph. Okay, so again, this is y equals b to the x, and just before we even go graphing it, we could tell it was a decay because our b is less than 1. Okay, and so if we look at the domain and we look left to right, it's still all real numbers. Or again, if you want to put -infinity to normal infinity. And then the range, we're looking at our asymptote. So it is the x-axis, so we're hitting everything bigger than 0. And again, it's not equal to 0 because it's never going to cross or touch the x-axis. In example 2, we're going to do the same thing. So -3 and then 2/5 to the x. So back to y equals and clear that one out. So -3 2/5 to the x power. And that wasn't in y equals, so let me do it again. So -3 alpha y equals 2/5 raised to x, and second graph it to pull up the table. And if we look here, our asymptote is getting very, very, very close to 0. Okay, but if we still just stick to -2 to 2, that will be enough to graph our exponential decay function. So we build our table once again and use just -2 to 2. So at negative 2, in this case, it was negative 18.75. At negative 1, it was negative 7.5, 0, negative 3, 1, negative 1.2, and at 2, negative 0.48. Or 48, not 5. There we go. Okay, so at negative 2, it is clear off the graph at negative 18.75. So I'll put it down here somewhere. At negative 1, it's a negative 7.5. Okay, 0, negative 3, 1, and negative 1.2. And at 2, it's almost negative a half the way down. So here, if we smoothly graph this one, okay, this is still decay, even though it's flipped over the x-axis or reflected. And the reason why it was reflected is because of that negative sign that was in the beginning. Okay, so it's still decaying, it's still falling from left to right, but it was just reflected. But now if we look at the domain, and left to right, well, it's still all real numbers. And the range, the asymptote is still approaching 0. So y equals 0, or the x-axis. But we're getting smaller in the y's. So this is going to be y is less than 0. And again, not equaling 0, because it's never going to touch or cross the x-axis. And one more here, we're going to do this one, again, by making a table of values. So in this case, this one was 3 times a half raised to the x plus 1. And make sure to tab out of the right because the minus 2 was tacked on the end. So this one will be shifted or translated on the coordinate grid because we have an h and a k, that plus 1 and the minus 2 on the outside. Okay, so second graph it to pull up the table. And if we keep going down, it looks like it's approaching negative 2. Okay, so if we, let's say, to get a good estimate from negative 3 to regular 3. Okay, so negative 3 to regular old 3. So at negative 3 it was 10, at negative 2 it was 4, then 1, negative 0.5, negative 1.25, negative 1.625, and negative 1.81, let's say. Okay, so if we go ahead and graph this at negative 310, okay, negative 2, 4, negative 1, 1, 0 and negative a half of a unit down, at 1, 1 and a quarter of the way down, 2, negative 1.6, at 3 it's getting even closer to negative 2. Okay, so if we connect these, okay, it's approaching the asymptote of negative 2. So again, our domain, if we look, we're left and right here, is just still all real numbers. We're hitting all the negatives and the positive x's, but the range in this case, our asymptote, is negative 2. And we're hitting everything above negative 2, but nothing below negative 2. So we're looking at all the y's greater than negative 2, but not equaling negative 2 because it's never going to cross the line of negative 2. And if you need help visualizing that, go ahead and make a dotted line as the asymptote to kind of help you guide your graph. And lastly, we're going to talk about exponential decay models. So when a real-life quantity decreases by a fixed percent each year, the amount y of the quantity after t years can be modeled by the equation here. Excuse me. So y equals a, and quantity 1 minus r with an exponent of t. Now this is different from the growth one by one major thing, and it's the minus sign in between in our growth factor, or decay factor in this case, because it makes sense that this is subtraction because it is decay, whereas the plus sign meant growth for the growth formula, okay? But a is still the initial amount, r is still the percent decrease expressed as a decimal, so that's still important, and 1 minus r is the decay factor. So an example 4 here, our last example, a new snowmobile costs $4,200. The value of the snowmobile decreases by 10% each year. We're first going to write an exponential decay model or formula. So I know we're starting out here, and we're going to figure out all of our variables. So A is our initial amount, which was the $4,200. And then 1 minus our percentage as a decimal. So 10, we put the decimal point on the end and move it 2 places every single time. It's just 0.10 or 0.10. Raised to how many years? And then that is the part 2 here after 3 years. And again, this is going to be approximate, and we're dealing with money, so we can have a decimal to the 100th to represent our cents. So second quit to get out of there, and we're doing 4,200, parenthesis 1 minus 0.10 for our 10% decrease, raised to the time, which is 3 years, and we have $3,061.80. So it's about $3,061.80.